So, in the last lecture we were deriving the temperature field inside and outside a particle which was placed in a constant temperature gradient far from the particle. Okay. So, we were considering a particle placed in a matrix. Okay. This is the z direction, and we have a constant temperature gradient or a linear temperature field far from the particle. Okay. T is equal to T prime times z. Okay. So, this is temperature, this is the z coordinate. Okay. And we used a spherical coordinate system where r was the radial coordinate, theta was the azimuthal coordinate. There was no variation in the phi direction. Okay. And if you recall, we had got the solutions for the temperature field as in the matrix temperature is equal to A n matrix by r power n plus 1 r power n plus B n matrix by r power n plus 1 P n of cos theta, n is equal to 0 to infinity, T particle is equal to sigma A n particle r power n plus B n particle by r power n plus 1 P n of cos theta. Those were the equations. Boundary conditions at r is equal to r, T particle is equal to T matrix, and the flux condition was minus K particle partial T by partial R is equal to minus K matrix partial T matrix by partial R. Okay. And for r going to infinity, okay, in the limit as r goes to infinity, the matrix temperature is a linear function. Okay. T matrix is equal to T prime z is equal to T prime r cos theta, okay, which is the same in a Legendre polynomial as T prime r P1 of cos theta, because cos theta P1 of cos theta is equal to cos theta. Okay. Because P1 of cos theta is equal to cos theta. Okay. So, that is what we had to solve. Okay. First thing I told you, in the particle, so there are two kinds of solutions here. The solutions multiplied by A n increases as r goes to infinity is 0 at r is equal to 0, except for n is equal to 0 where it is a constant. Those are the growing harmonics. The solutions proportional to r power 1 by r power n plus 1 are what are called the decaying harmonics. They decay, they decrease as r goes to infinity, and they go to infinity at r is equal to 0. For the temperature field to be finite at r is equal to 0, for the particle we require that this term is equal to 0. Okay, we require that this term is equal to 0, because otherwise the temperature field will diverge in the particle as r goes to infinity. Further, we were looking at the temperature field due to the Legendre polynomials. Okay. So, this solution T prime, okay, Tm can be written as summation of, okay, Cn r power n Pn of cos theta. Okay. N is equal to 0 to infinity for r much larger than 1. Okay. If you write it this way, then you get a series of coefficients out of which C0 is equal to 0, C1 is equal to T prime, C2 is equal to 0, etc. Okay. Since all the Legendre polynomials are all orthogonal to each other, okay, since all the Legendre polynomials are all orthogonal to each other, right, in this series expansion, we can equate terms at each value of n. Okay. In this series expansion, we can equate terms at each value of n in the boundary conditions. Okay. Okay. So, at r is equal to r, right, the boundary condition for the temperature is that sigma n is equal to 0 to infinity a n r power n plus, that is the matrix, plus b matrix n by r power n plus 1 p n of cos theta is equal to the summation is equal to the summation n is equal to 0 to infinity a particle n r power n plus b particle n by r power n plus 1, okay, p n of cos theta. Okay. That is the equal temperature boundary condition. Okay. However, since all the Legendre polynomials are orthogonal, I can multiply the left and right sides by p m of cos theta, okay, and I will get delta functions, right. Therefore, each of these are equal at each term in the expansion. For each value of n, the left side has to be equal to the right side, because the basis functions are all orthogonal. Okay. The Legendre polynomials are all orthogonal, the basis functions are all orthogonal. Therefore, the left and the right sides have to be equal for each value of n, that is a n matrix r power n plus b n matrix by r power n plus 1 is equal to a n particle into r power n, and I already told you that this b n's all have to be 0 in the particle, so that the temperature is finite. Okay. So, this has to be true for each value of n. Okay. Similarly, the flux conditions also have to be true for each value of n, right. So, I will get minus minus k matrix times partial by partial r. I will get a n matrix n r power n minus 1, okay, okay, plus b n matrix into minus n minus 1 by r power n plus 2. Okay. I have taken the derivative and I have substituted r is equal to r at the surface. Okay. So, is equal to minus k particle times this derivative, okay, term by term, okay, a particle n into r power n minus 1. Okay. So, at each value of n, the left side and the right side have to be equal within the at the interface between the particle and the matrix. Okay. So, those are the two boundary conditions at the interface. There is a third condition here, as r goes to infinity, right, the matrix temperature, okay, sigma a n matrix r power n plus b n matrix by r power n plus 1 p n of cos theta is equal to sigma c n r power n p n of cos theta. Okay. N is equal to 0 to infinity. And I had argued that since the Legendre polynomials are all orthogonal to each other, this has to be satisfied for each value of n. Okay. So, this has to be satisfied for each value of n. Okay. So, this has to be true for each value of n, okay, because the Legendre polynomials are orthogonal. I can multiply both sides by m and I will get an equation in terms of m for each individual value. Okay. Okay. So, this is the boundary condition as r goes to infinity. Okay. As r goes to infinity, obviously the decaying harmonics go to 0. Okay. Obviously, as r goes to infinity, okay, as r goes to infinity, these decaying harmonics will all go to 0. And therefore, I will get a n m r power n is equal to C n times r power n, which basically gives you that a n m is equal to C n, okay, where C n is the term in the boundary condition, in this expansion in the boundary condition. Okay. So if I write this as summation of C n r power n p n of cos theta, okay, expand in the Legendre polynomial expansion, then I told you that for this particular case C 0 is equal to 0, C 1 is equal to t prime, C 2 is equal to 0, etc. Okay. There is a non-zero value only for n is equal to 1. So, let us examine what happens when n is not equal to 1. Okay. Okay. When n is not equal to 1, A matrix n is equal to 0, okay, because for n is not equal to 1, all of these coefficients are all 0. Okay. When n is not equal to 1, all of these coefficients are 0. Therefore, A n matrix is equal to 0 for n is not equal to 1. Okay. And if A n matrix is equal to 0, you can see that these two equations are basically two linear equations for A n particle and B n matrix. These are linear equations for A n particle and B n matrix. You can solve these equations quite easily. In fact, you can see that if you put A n matrix is equal to 0, B n matrix is equal to 0 and A n particle equal to 0, these equations are all identically satisfied. Okay. These equations are identically satisfied. Therefore, for n is not equal to 1, where the boundary conditions as r goes to infinity is identically 0, all of these coefficients are 0. Okay. Therefore, the only terms that are non-zero in this case are for the matrix is equal to A 1 matrix r plus B 1 matrix by r square P 1 of cos theta, and T particle is equal to A 1 particle r P 1 of cos theta. B 1 particle was 0 because temperature had to be 0 at the origin. Okay. That is because the only non-zero term is for and from this equation I get, okay, A 1 matrix is equal to T prime. Okay. Because you can see that C 1 is equal to T prime, C 2, C 0, C 3, etc., they are all 0. Okay. So, all the coefficients in this series n is equal to 0 to infinity, all coefficients are 0 except for n is equal to 1, because for n is not equal to 1, there is no forcing of the temperature field as r goes to infinity. The only forcing is in the form of P 1 of cos theta times r. Okay. Therefore, the response also has to be proportional to P 1 of cos theta, because all the Legendre polynomials are all orthogonal to each other. So, if there is no forcing in P 2, P 3, etc., the only solution you will get is that A 2, A 3, etc., they are all identically 0. Okay. If there is no forcing in P 2, P 3, etc., the only solution you will get is that A 2, A 3, etc., they are all identically 0. Okay. Therefore, the only term that survives is n is equal to 1. That is because of the orthogonality of the Legendre polynomials. The equations are del square of t equal to 0, right. They have no forcing in them, they are just Laplacian of the temperature is 0. Boundary conditions at the surface are equal temperature, equal flux. Okay. Whatever is the temperature on both sides has to be equal, the flux has to be equal, no forcing there, no inhomogeneous term there. Origin also there is no inhomogeneous term. The only inhomogeneous term is for r going to infinity, and at r going to infinity the temperature field is of the form T prime times r times P 1 of cos theta. And since P 1 of cos theta, the Legendre polynomials form an orthogonal basis set, the solution is also of the form P 1 of cos theta. Okay. So, therefore, only the first term in the expansion survives. The 0th term coefficient has to be equal to 0 because there is no forcing far away, the second term and so on. Okay. Okay, fine. So, now we have to satisfy use these conditions. Okay. So, I can since A1m is T prime, I can just substitute here. Okay. T prime r plus B1 m by r square P1 of cos theta, and temperature in the particle is A1 particle r times P1 of cos theta. So, just based upon the symmetries, or rather the orthogonality of the Legendre polynomial series, the orthogonality, each term in the series is orthogonal to every other term. That means that if the forcing is in the form of P1 of cos theta, the response throughout the domain can only be of the form of P1 of cos theta, because for all the other P2, P0, P3 etc., the forcing is 0. And if you apply the boundary conditions, you will find that the boundary conditions as well as the conditions at infinity are identically satisfied if the coefficients are all 0. Okay. So, the only forcing is of the form of P1 of cos theta. Okay. So, now that I have this, I have to find out the coefficients A1p and B1m. Okay, and those come from the boundary conditions at okay. Note that I have already enforced the boundary condition as r goes to infinity. That is why this term is equal to T prime. In the limit as r goes to infinity, I get the matrix temperature as T prime r P1 of cos theta. I have already enforced the boundary conditions at r is equal to 0 within the particle. The condition that the temperature field has to be finite at r is equal to 0 implied that all of the decaying harmonics of the form B particle n by r power n plus 1 P n of cos theta, all of the coefficients in this has to be 0, so that the temperature does not diverge at the origin. Okay. And now I have to enforce the interface boundary conditions. Okay. Now I have to enforce the interface boundary conditions. Okay. At r is equal to r, T particle is equal to T matrix. Okay. That means that A1 particle r is equal to T prime r plus B1 matrix by r square. Okay. And the second condition is that minus k particle partial T particle by partial r is equal to minus k matrix partial T matrix by partial r. Okay. So, this gives me minus k particle into partial T particle by partial r is just A1 particle is equal to minus k matrix into T prime minus B1 matrix by 1 over r square is minus 2 by r cubed. Okay. Okay. There is a P1 of cos theta on both sides, that will cancel out on both sides. Okay. What I can do is divide this equation for the flux throughout by Km to get an equation of the form Kr A1 particle is equal to T prime minus 2 B1 m by r cubed. Okay, where Kr is equal to K particle by K matrix. That is the relative conductivity. Okay, that is the relative conductivity of the particle and the matrix. So, these two equations, okay, first one is for the temperature field. Okay, first one is for the temperature field. The second one is for the flux. These have to be solved to obtain A1 particle and B1 matrix, these equations do have an inhomogeneous term, and that is this t prime here. Okay. So, you get a non-trivial solution. If this term had not been there, it is not there for n is equal to 0 or n is equal to 2 or n is equal to 3, because there is no forcing at infinity. If this term is not there, then the only solution is that the coefficients are all 0. But since this term is present, you have a non-zero solution, okay, and you can get that solution easily. Okay. So, the solution is of the form A1 particle is equal to 3 t prime by 2 plus k r, and B1 matrix is equal to 1 minus k r cubed, okay, t prime by 2 plus k r. Okay, so, that is the solution, okay, for the temperature field. Okay. So, therefore, the temperature field in the particle is equal to 3 t prime r P1 of cos theta by 2 plus k r, and in the matrix temperature is equal to t prime, okay, plus 1 minus k r, sorry, t prime r plus 1 minus k r cubed t prime by 2 plus k r. Okay. This t prime r is the temperature as r goes to infinity, and this term is the correction due to the presence of the particle, okay, into P1 of cos theta. There should be a 1 over r square. Okay. T prime r plus 1 minus k r cubed t prime by 2 plus k r into r square. Okay. The growing harmonic increases proportional to r, the decaying harmonic decreases proportional to 1 over r square. So, these are the two solutions. We can verify consistency. Okay. If the relative conductivity K r is equal to 1, it is equivalent to having just a uniform system. If K r is equal to 1, it is equivalent to having a uniform system. There should be no temperature disturbance. And you can see that for K r is equal to 1, T p is equal to, okay, t prime r P1 of cos theta, and T m is also equal to, okay, that factor of 1 minus k r becomes 0, t prime r cos P1 of cos theta. Okay. So, in this particular case you have no temperature disturbance and it is equal to having just a uniform system. So, that verifies the consistency of the formulation. Okay. And you can plot these temperature fields. Okay. If K r is greater than 1, the thermal conductivity of the particle is greater than the thermal conductivity of the matrix. Okay. This term 1 minus k r cubed t prime by 2 plus k r into r square turns out to be negative. Okay. What that means is that if I have a temperature field like this is the z axis. Okay. If the matrix thermal conductivity is larger than the particle thermal conductivity, then this second term is negative. Okay. That means that in the radial direction the temperature field, the temperature gradient is negative for z going from 0 to pi. So, you will expect the temperature field to come like this. Okay. And on the other side it goes like this. Okay. In between, in the particle, the temperature field is just proportional to z itself, because r times P1 of cos theta is the same as r cos theta, which is the same as z. So, within the particle you have temperature field that looks like this, and it comes in and goes out. Okay. Okay. Comes in for theta between 0 and pi, because this term here is negative, and goes out for theta between pi and 2 pi. It goes outward in the radial direction. Okay. So, In this direction the flux lines will come this way, and in this direction the flux lines will come in this direction. Okay. And the opposite happens if Kr is greater than 1. Okay. So, that is the final result for the temperature field. Okay. So, I have now got the temperature field around a single particle. Okay. I have now got the temperature field around a single particle. Recall that our original problem was to determine the temperature field due to a composite, okay, due to a large number of particles, okay, due to a composite, okay, with spherical inclusions in it. We had to determine the temperature field and the average flux. Okay. In the non-interacting limit, where the temperature field around one particle does not affect the temperature around another particle. Okay. So, this average flux can be written as a volume average, for example. The volume average will give you the average flux passing through the entire system. Okay. Integral dV of the flux in the z direction. Okay. This I can use the constitutive relation to write this as 1 over V integral dV of minus k partial t by partial z. Okay. Note that in this volume there are two kinds of materials, one with conductivity Kp and the other with conductivity Km. Therefore, this average has to be carried out over both of them. Okay. So, this has to be 1 over the total volume times integral over the particles okay, plus the integral over the matrix. Okay. So, that is the total flux. Okay. Okay. So, now we have the temperature field in the particle, we have the temperature field in the matrix, okay, and we have to calculate the total flux. Okay. Once we calculate the total flux divided by the total volume, we will get the average flux, and that will be related in some way to the relative conductivity between the particles and the matrix. So, this calculation of the average flux I will continue in the next lecture. I will see you then.